Hi all, welcome back to my channel. Let us start with a new class. Today's topic is Boolean Algebra. There are two topics coming under this chapter. They are Boolean functions and its representation, simplification of Boolean function. Both are very simple topics. Now let us start with Boolean Algebra. Boolean Algebra is an algebra that deals with binary variables and logic operations. The variables are designated by letters such as A, B, X and Y. In mathematics and mathematical logic, Boolean algebra is the branch of algebra in which the values of the variables are the truth values true and false, usually denoted by 1 and 0 respectively. Boolean algebra was invented by George Boole in 1854. Three basic operations are and, or, and not. And or conjunction denoted x and y satisfies x and y equal to 1 if x equal to y equal to 1 and x and y equal to 0 otherwise. Or disjunction denoted x or y satisfies x or y equal to 0 if x equal to y equal to 0 and x or y equal to 1 otherwise. Not or negation denoted negation of x satisfies negation of x equal to 0 if x equal to 1 and negation of x equal to 1 if x equal to 0. Boolean functions. A Boolean function can be expressed algebraically with binary variables, the logic operation symbols, parenthesis and equal sign. For a given value of the variable, the Boolean function can be either 1 or 0. Consider, for example, the Boolean function f equal to x plus y dash z. The function f is equal to 1 if x is 1 or if both y dash and z are equal to 1. F is equal to 0 otherwise. Boolean expression. A Boolean expression always produces a Boolean value. A Boolean expression is composed of a combination of the Boolean constant, Boolean variable and logical connectives. Each Boolean expression represents a Boolean function. Example, a b dash c is a Boolean expression. The relationship between a function and its binary variables can be represented in a truth table. Truth table is a table that contains all possible values of logical variables in Boolean expression. To represent a function in a truth table, we need a list of the 2 power n combinations of the n binary variables. As shown in the figure, there are 8 possible distinct combinations for assigning bits to the 3 variables x, y and z. The function f is equal to 1 for those combinations where x equal to 1 or yz equal to 0, 1. It is equal to 0 for all other combinations. A Boolean function can be transformed from an algebraic expression into logic diagram, a logic diagram composed of and, or and inverter gates. The logic diagram for f is shown in the figure. There is an inverter for input y to generate its complement y dash. There is an AND gate for the term y dash z and an OR gate is used to combine the two terms. In a logic diagram, the variables of the function are taken to be the input of the circuit and the variable symbol of the function is taken as the output of the circuit. Representation of Boolean function. We can represent Boolean function in 3 forms, that is sum of product or SOP, product of sums or POS and canonical form. Canonical form again include standard SOP and standard POS. First one is sum of product form, also known as SOP. See, the definition here is SOP is a group of product terms summed together. For example, f of ABC equal to AB plus AB dash C plus BC. This expression is in SOP form. Here, product terms are added together. This is also called disjunctive normal form. Next form is product of sums or POS. The definition here is POS is a group of sum terms multiplied together. For example, f of ABC equal to a plus b into b plus c. This is also called as conjunctive normal form. Canonical form, standard SOP and standard POS. If you want to represent any Boolean expression in terms of canonical form, you are having two forms in that is standard SOP form and standard POS form. Standard SOP. Each product term contains all the variables of the function f of ABC equal to a dash bc plus a b dash c. This is a three-variable function. The expression for this function having two product terms. Whenever each product term contains all the variable, then we call it as in standard SOP form. Now come to standard POS. This is also similar. Each sum term contains all the variable of the function. For example, if we are having POS form, if that expression contains all the variable of the function, then that is said to be in standard product of sums form. Example, f of ABC equal to a dash plus b plus c into a plus b dash plus c. Minterms and max terms. In Boolean algebra, while solving Boolean expression and K-maps, we are going to hear some words like minterms and max terms. So what is meant by a minterm and what is meant by a max term? That we will discuss now. So minterm is nothing but each individual product term in standard sum of product form. Similarly, max term is each individual sum term in POS form. For example, for a two-variable function f of ab with two variables a comma b, the combinations are 0, 0, 0, 1, 1, 0 and 1, 1. These are the possible four combination for a two-variable function. Now we will see how we are going to write minterms and max terms. Minterms is nothing but product terms. Whenever 0 is there, we are taking the complement of actual variable, and whenever 1 is there, we are taking actual variable. Whereas in max terms, when 0 is there, we are taking actual variable, and when 1 is there, we are taking complement. See here how we are going to write minterms and max terms for a two-variable function. If your function represents 0, 0, then the minterm may be a bar, b bar. This is also called m0 minterm, that is minterm 0. Now, if the function represents 0, 1, the minterm is a bar b, that is m1. Similarly, the function represents 1, 0, the minterm is a b bar, that is m2. Now here we are having 1, 1, the minterm is ab, that is m3. We usually use small letter m to represent minterms. In the same way, we can write max terms. But when we are writing max terms, please keep in mind that when 0 is there, we are taking actual variable, and when 1 is there, we are taking complement. And between the variable, we need to consider addition. If the function represents 0, 0, the max term is a plus b, that is m0. And 0, 1, the max term is a plus b bar, that is m1. Similarly, the function represents 1, 0, the max term is a bar plus b, that is m2. And 1, 1, the max term is a bar plus b bar, that is m3. We usually use capital letter M to represent max terms. So, this is about two variable minterms and max terms. Now we will see how we are going to represent the function and minterms and max terms. Consider the function f of ab equal to ab plus a bar b. This is in SOP form. In ab, we are having both a and b. Similarly, in a bar b, we are having a and b. From this, how we can write minterms means m of m3, m1. That is sigma m of 3, 1. Seeing this summation itself, you can say these are minterms. Binary for 1 is 0, 1 and binary value of 3 is 1, 1. 0, 1 we can represent a bar b and for 1, 1 we can represent ab. Dual of this expression is f of ab equal to a plus b into a bar plus b, which is equal to 0, 0, 1, 0, 0, 0, m0, 1, 0, m2. Representation of max term is pi of m 0, 2. Binary for 0 is 0, 0. Binary for 2 is 1, 0. That is a plus b, a bar into a bar plus b. Basic laws of Boolean algebra. These fundamentals are very important when we are solving Boolean expression. To solve any Boolean expression, we need to apply these fundamentals. First one is identity law. X plus 0 equal to x, x dot 1 equal to x. For example, if x equal to 1, 1 plus 0 equal to 1. If x equal to 0, 0 plus 0 equal to 0. Whatever value of x is taking, that is coming into the output. Here 1 and 0 are logic 1 and logic 0. The variable x can take both the values 1 and 0. Similarly, x dot 1 equal to x. If x equal to 0, 0 dot 1 equal to 0. If x equal to 1, 1 dot 1 equal to 1. That is, whatever value of x is taking, that is coming into the output. Next is complement law. X plus x dash equal to 1. If x is the variable, then x dash is the complement of that variable. If x equal to 0, x dash equal to 1. That is 0 plus 1 equal to 1. If x equal to 1, x dash equal to 0. That is 1 plus 0 again equal to 1. Similarly, x dot x dash equal to 0. That is 0 dot 1 equal to 0, 1 dot 0 equal to 0. The third one is idempotent law. X plus x, the answer is x, and it is obviously 0 plus 0, the answer is 0. 1 plus 1, the answer is 1. In case of multiplication, x dot x is x. If you are multiplying 1 and 1, the answer is 1. And if you are multiplying 0 and 0, the answer is 0. Next one is dominance law. In law of addition, x plus 1 equal to 1. And in law of multiplication, x dot 0 equal to 0. In the first case, when x equal to 0, 0 plus 1 equal to 1. When x equal to 1, 1 plus 1 equal to 1. Because here in Boolean algebra, 1 and 0 are not binary values. They are logic values. In second case, the law of multiplication, x dot 0 equal to 0. Any number multiplied by 0 is 0. That is x dot 0 equal to 0. If x equal to 0, 0 dot 0 equal to 0. If x equal to 1, 1 dot 0 equal to 0. The next one is invaluation law. X complement all complement equal to x. If x equal to 0, x complement equal to 1, x complement all complement equal to 0. That is equal to x. If x equal to 1, x complement equal to 0, x complement all complement equal to 1, which is equal to x. Next is commutative law. Commutative law states that the interchanging of the order of operands in a Boolean equation does not change its result. For example, in law of addition, x or y equal to y or x. Similarly, in law of multiplication, x and y equal to y and x. Next is associative law. X or y or z equal to x or y or z. It deals with how we can associate the variable in a relation. For example, x added with y or z is equal to x or y added with z. In the similar way, in multiplication also we can write x and y and z equal to x and y and z. Next is distributive law. Distributive law in law of addition state that x and y or z equal to x and y or x and z. In law of multiplication, x or y and z equal to x or y and x or z. Next is De Morgan's law. This theorem is very important throughout solving Boolean expression. De Morgan's law states that x or y all complement equal to x complement and y complement. Similarly, in law of multiplication, x and y all complement equal to x complement or y complement. Next is absorption law. This law enables a reduction in a complicated expression to a simpler one by absorbing like terms. For example, absorption law in law of addition states that x or x and y equal to x. Similarly, in law of multiplication, x and x or y equal to x. We can simplify some expressions using these rules. Now let us do a couple of examples. Match the following identities or laws to their corresponding name. List 1. A. X or x equal to x, x and x equal to x. B. X or 0 equal to x, x and 1 equal to x. C. X or 1 equal to 1, x and 0 equal to 0. D. X and x or y equal to x. List 2. Dominance law, absorption law, idempotent law and identity law. Option A is A3, B4, C1 and D2. Option B is A4, B3, C1 and D2. Option C is A4, B3, C2 and D1. Option D, A3, B4, C2 and D1. The correct answer is option A, A3, B4, C1 and D2. Now let us check the solution. X or x equal to x, x and x equal to x. This is idempotent law. X or 0 equal to x and 1 equal to x. This is the identity law. X or 1 equal to 1, x and 0 equal to 0. This is dominance law. X and x or y equal to x is absorption law. Simplify C plus BC all bar. The given expression is C plus BC all bar. Using De Morgan's law, we can write BC all bar equal to B bar plus C bar. That is C plus BC all bar equal to C plus B bar plus C bar. Commutative law states that B bar plus C bar equal to C bar plus B bar. Applying associative law, we can write C plus C bar plus B bar. By applying complement law, C plus C dash equal to 1. That is 1 plus B bar, which is equal to 1 applying identity law. Simplify A plus C into AD plus AD bar plus AC plus C. The given expression is A plus C into AD plus AD bar plus AC plus C. A is the common term in AD and AD bar. So applying distributive law, the expression becomes A plus C into A into D plus D bar plus AC plus C. By applying complement law, D plus D bar equal to 1. Applying identity law, A dot 1 equal to A. That is, the expression is A plus C into A plus AC plus C. By applying commutative and distributive law, the expression becomes A into A plus C plus C plus C. By applying associative law, A plus C equal to A plus C plus C. Applying idempotent law, C plus C equal to C. That is, the expression become A into A plus C plus C. By using distributive law, the expression is A into A plus AC plus C. Idempotent law state that A dot A equal to A. By applying distributive law, AC plus C equal to A plus 1 into C. That is, the expression is A plus 1 into C. Applying dominance law, a plus 1 equal to 1 by applying identity law c dot 1 equal to c. So the expression become a plus c. That is, the simplified form of the expression is a plus c. If you like this video, hit the like button and subscribe my channel. If you have any query, you can ask in the comment section. Do subscribe to this channel in order to get notified when I am posting a new video. Thanks for watching.